Hello, students. Today I am here with a section of physics which deals with atom, its structure and characteristics. We already know that the matter consists of atoms. This concept was first given by Dalton, and the structure of the atom was proposed by J. Thomson. Later, the structure was modified by Rutherford and then by Niels Bohr. You already know that earlier the structure of atom that proposed by Thomson was assumed as a sphere of radius of the order of 10 to the power minus 10 meter, in which entire mass and positive charges were uniformly distributed, and the negative charges, the electrons, were embedded like seeds in watermelon or like plums in the pudding, as shown in the diagram. That is the reason the Thomson model of atom is sometimes called the plum pudding model. This model also suggested that the atom is electrically neutral since the number of positive and negative charges are equal in the atom. But the model could not explain the spectral lines of hydrogen and other atoms observed experimentally. We know that matter radiates electromagnetic radiations due to vibrations of atoms and molecules. So, an element is associated with a characteristic spectrum of radiation. The Thomson model could not explain why an atom like hydrogen, consisting of a single electron and a single proton, emits a complex spectrum of discrete wavelengths. We see hydrogen always gives a set of lines with fixed relative position between the lines. Thomson model also could not explain the large angle scattering of alpha particles from thin metal foils, that is Rutherford scattering. Later, Rutherford, on the basis of the result of alpha particle scattering experiment, modified the concept of structure of an atom. It actually led to the discovery of atomic nucleus. So, first we will see the details of alpha particle scattering experiment and then the conclusions. You know that an alpha particle is a helium nucleus with 2 protons and 2 neutrons. Hence, it has 4 units of mass and 2 units of positive charge. There are many radioactive elements that emit alpha particles. Here you see the experimental arrangement in given diagram in which radioactive source of alpha particles, bismuth 21483, is placed in a lead cavity. The emitted alpha particles are collimated into a narrow beam using lead slits called collimator. The collimated, that is parallel beam of alpha particles, is allowed to fall on a thin gold foil having thickness of the order of 10 to the power minus 8 meter. It is nearly equal to 2.1 into 10 to the power minus 7 meter. The alpha particles are scattered in different directions, which are observed through a rotating detector consisting of a zinc sulfide screen and a microscope. When the scattered alpha particles strike the zinc sulfide screen, that is fluorescent screen, bright flashes of light called scintillations are produced, which are detected through the microscope and counted at different angles from the direction of incidence of the beam. The angle of deviation of an alpha particle from its original direction is the scattering angle theta. Now see the graph plotted between the scattering angle theta along x-axis and the number of scattered alpha particles n theta along y-axis. The explanation of the results led to the nuclear model of the atom. It is clear from the graph that most of the alpha particles pass straight through the gold foil, which means they suffer very small angle of scattering. We also see that very few alpha particles scatter through large angles, that is more than 90 degree, and very rarely an alpha particle rebounces, that is scattered through an angle of 180 degree. The scattering of alpha particles is due to Coulombian interaction with positive charges and electrons in every atom of the gold foil. The scattering angle theta would be very small if positive and negative charges were distributed uniformly in an atom. And the results of the observation in alpha particle scattering experiment was quite different from the assumptions of the Thomson's model. An alpha particle is 7,000 times more massive than an electron, and in this experiment alpha particle moves at high speed. Therefore, very strong forces alone could have deflected them through large angles. This fact led Rutherford to postulate that the entire positive charge of the atom must be concentrated in a tiny central core of the atom, which was termed as atomic nucleus. The conclusion derived from the observations is that the scattering of alpha particle depends on its distance from the nucleus of the atom, which you can see in the diagram called impact parameter B of collision. This impact parameter is the perpendicular distance of the direction of the initial velocity of alpha particle from the center of the nucleus. In the diagram, you can see the alpha particles with different impact parameters being scattered in different directions. An alpha particle close to the nucleus, which has a small impact parameter, suffers large scattering, while that having large impact parameter suffers small scattering. Finally, we observe that the alpha particle that tends to collide head on with the nucleus slows down due to very strong repulsive force offered by the nucleus and stops, and then bounced back, retracing its path, the scattering angle being 180 degree. The alpha particles which pass close to the nucleus experience comparatively smaller repulsive forces and get deflected through large angles, theta being greater than 90 degree. The alpha particle which passes at greater distance from the nucleus experiences much smaller force of repulsion and hence deflected through a small angle, theta being less than 90 degree. It is thus concluded that the scattering of alpha particles depend on its distance from the nucleus of the atom. An alpha particle passing at much larger distance from the nucleus go almost undeviated. This result led to the size of the nucleus. For calculation of the nuclear dimensions from alpha particle scattering experiment, Rutherford made certain assumptions that we will see in the next class while calculating the distance of closest approach of the alpha particle from the nucleus. We will also see the success and drawbacks of the Rutherford's model followed by Bohr's model of the atom. Okay then, see you in the next class.